Hello everyone and welcome to this new episode of EagleFly, the experimental debugger. Today we will continue with Disassembler, and if you like to follow along, please don't hesitate and welcome. If you have any questions about the project, any inquiries you may ask, you can post them on Twitter or YouTube and I'll be there to answer. With that said, let's start by opening the project. Okay, so the last thing we did was that we were reading the ISA. I believe we got until here where we were just looking at the transcendental instruction accuracy, which is a way to well we didn't understand too much of it, but we know that it's how much of an error it happens to be computed when using transcendental instructions like f sine, f cosine, f sine cosine, f p tangent, well, all these instructions, f p tangent, f2 xmi, all these instructions happen to have an error equal to fx minus, I don't know what they mean by each one of these. Oh, okay. So yeah, the correct and complete approximate function values. So it's pretty much the difference between both of them. The difference between both values gives an error, then divided by by like some kind of like an average. It's 2 to the k minus 63, where k is an integer such that 2 to the minus k, it's times the correct value with correct accuracy. It's in between the range 1 and 2. Okay. That means that fx has to be on the range of it depends, because if it's 2 to the k, let's see, we have fx 2 to the k, that has to be greater than 1 and less than 2, greater than or equal than 1 but less than 2. That means that fx has to be 2 times fx has to be less than 2 times 2 to the k, and it has to be less than 1. Well, you can, and 2 to the k probably, because as I say 2 to the k, then I change this and then 2 to the k. So yeah, fx is between the range of 2 to the k to 2 times 2 to the k. So That means that the range of fx is 2 to the k. You get it? Which, I mean, 2 to the k, 2 to the k, how do you choose k? Do you choose it arbitrarily? I don't know. We have to read a little bit more about precision and how do we compute precision. Fortunately, we have a good book about that. That Mr. Casey Muratori talked about it when he was when he on one of his shows on one of the series of the Hero series, and if I believe it should be here somewhere. Here you go. This book specifically talks about it. Now let me floating point arithmetic. It's a good book about floating point, which is basically what we are talking here. How the precision works and stuff like that. And if we want to go deeper, well, we can just go with the other books about how to make numerical computation and stuff like that, which would be nice, of course. But yeah, for now we are just gonna keep it that way, simple. Later on, we can see if we can dig a little more deeper on how floating point computation error accuracy can be minimized. Well, yeah, and how can we minimize the error of computations, which they tell, I mean, pretty much they tell us some kind of summary here where you can, I mean, you keep the values of the radians less than p 3 pi 4s, for some cases, or less than 3 pi divided by 8s in other cases, but why does why does that happen to be the case? We have to dig a little bit more deeper in. So yeah, so there's control instructions. That's another case for this. Waiting for the okay. Floating point exception handling. Okay. So I think we can start by disassembling this stuff. I mean, of course, this is also something we're gonna come back to this once more. Just let's try to read onto here, and we go back to the code and do some stuff there. These instructions are commonly used when switching tasks or contexts. Hold on a second. Okay, so basically, okay, so there are different mnemonics. The only meaning is that some they wait, some they don't. Yeah. Store control word with waiting or without waiting. Store status word the same way, waiting or not waiting. Uh, Clear the exception flags, without waiting or not waiting. This is kind of interesting because the exception flags are the ones that we are looking for. So if we wait for them and then clear it, that makes sense. But sometimes we don't want to wait. Just clear the value. We don't want to handle the exceptions that are unmasked. FCLX, F and CLX. If you see, normally when we make loading, loading doesn't allow any it doesn't wait when we load. It's just do the loads. It's more when we store the values is when we rather wait for the exception handling, if any. performs no specific operation and no internal x87 FPU states are affected. What does no specific operation happens? It's like no operation or what? Okay, so yeah, I mean, exception handling is something that we're gonna wait until we got to the point we go back to the debugger and stuff. For now, we don't care too much about that, so let's go back to the thing where we the disassembler now. We're gonna make the disassembly of, let's see, for this escape opcode instruction. So you see the first byte is between the range of an escape opcodes, which is it was D8DF. I'm sorry. And okay, so these are the instructions: format certain codes if string, BP align, control transfer instructions, and the other stuff. So let me kind of save this. Well, we don't care about this. Let me go back to here. Server interrupt instructions. There we go. These are GPR instructions, which we will do later. So yeah, so I will pick up here. I will copy this. I go here, and we're looking for DD. So DD is here. Table blah 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 contains maps for escape instruction subcodes that begin with DDH. Table A17 shows the map if the model RAM bytes in the range of OBFH. Oh, okay. So wait a second. So yeah, it was because if it's, let me remember it, if it was in BFH, from 00 to BFH, the encoding was on the rec, or in this case the NNN field. But if it's from greater than BFH to FFH, or let's say from C0 to FF, the whole model RAM would be an extension of the rec field. Which is I mean, it's just like defining, well, yeah, both of them are extensions, but they can be, one occupies shows the rec field and the other occupies the whole model RAM set to define a new set of instructions. So For example, for DD, where is it? This is, I'm gonna keep it here. Samples are provided below. Okay, perfect. So we go to DD. Let's say that, well, we can use this one. So we have DD, and now we have 05, so that means that it's between the range of 00 to BF. So that means that we only have to check for the extension into the NNN field, which is 05, so it has to be 101. Oh my god. There's nothing in there. Oh my god. Oh no, sorry. 05 is the model I'm by, but 05, it's, well, it's 101. That means that it's 000, so that means that we have a FLD, you know, double real. We're gonna load the value into the ST0. That remember, FLD. Let me go here. Let's go back into our table. Yeah, FLD. There we go. This is the, oh, okay. So FLD with D9 is a single reel. You know, we're gonna load a single reel, but FLD, the other, is a double reel. Okay. So load constants, if load pi, load, yeah, control instructions, load control war, load FLD. Okay, yeah, we're loading a value, you know, here we go, it's correct. FLDEM, load environment, FLD, it's undefined for the control codes, and it can be 0 or, you know, depends. It depends. Normally it will be 0 or the interrupt handler. Now FLD control war, we don't care about that. I want the instruction. Probably there's gonna be a lot of them. Low floating point, yeah. Yeah, because remember, we have two instructions. We have FLD and FILD, which loads an integer. So FLD just cares about floating point operands that can be single or double precision, and any of both cases will be converted onto double extended precision when passed to the stack register. So register stack, the x87 register stack. Okay, so yeah, that's good, we know that. We want to see the actual instruction. Single and double, that's an arithmetic. Load floating point, I don't know where I am. Oh, the exceptions, okay. Okay, single or double, floating point. float environment instruction. Where am I? Okay, we are on the guidelines for an FPU exception. Okay, that's good. We don't care about that. And if we're storing state, oh my god, where is the instruction? Where is the instruction? Where is the instruction? Here we go. There you go. So normally they can be D9, DD, DB, or D9, C0. And we're gonna have 0, 0. And this uses 0, 0, you know, extension. We have DB with 05. This loads an 32 floating point, 64, and this is an extended one, 80 floating point. And this loads to SDI, which indeed has a nice property, which is D9C0 plus I. That's good. And then 64-bit mode, valid. That compile, okay, push M32 onto the FPU register stack, push M64, blah blah blah, if on the register stack, push SDI onto the FPU registers. Oh, okay, my bad. Yeah, it's we push something that's already on the register stack, but we push it on top of the register stack. That's pretty much what it does. Source operand typically register stack. Source operand can be single precision, double precision, same precision, for format. The source operand is in the single precision. It is automatically converted to the double state precision for implement format before being the push on the stack. The FLD instruction counts to push the value in a selected FPU register onto the stack. Here, pushing register ST0 duplicates the stack top. Okay, that's interesting. This instruction's operation is the same in non-64-bit modes and 64-bit mode. This is the flag set to 1 if stack overflow occur, otherwise set to 0, C0, C2, C3 undefined. That's correct, that's what we saw. Basically, underflow or overflow occur. Source operand is in SNAN, does not occur if the source operand is in double extended precision floating point format, FLD, MADFP, or FLD STR. Okay. Source operand is at the normal value, does not occur if the source operand is in double extended precision floating point format. Okay, perfect. GP0, protectable exceptions. Okay. It's a GP is occasionally located in a non-readable segment. If a memory operand affected to address is outside the ECS, DSES, FS, GSM, actually. Okay, the DSS, okay. It's outside the SCS, DSES, FS, or segment limit. If the DSES, FS erase reduced access memory and it contains a non-segment selector. Okay, if a memory operand okay. Oh, that's interesting. So even if the destination is non-readable, even we are just reading from the load, I believe this happens. Okay. If a memory operand effective address is outside the SS segment limit, Oh, okay. I was like, what? We have load 1, load 2 T, load 2 E, load 2 pi, load G, 2 load and 2 load C. Yeah, these are the other ones, but these are constants. Okay, okay. So yeah, I mean, I was just like trying to see what was the exact meaning of it. So we go back here. We have a double real. We know that. So we go back into here. We know about it because extension does something about it. Now, since the mother and byte so far edge within the yeah, it's between the 00H through BFH range. Bits 35000. This will indicate the opcode for an FLD double real instruction. See table A now. The double real value to be loaded is at 004H because since it's a little endian, we have to make the translation now to be changed that way. The 32-bit displacement that follows and belongs to this opcode. Okay, that's all. Is that all? Okay, so let's go to the code. Let's go back and do that because yeah. So let's add the instruction string first, which we can do it pretty easily. Here you go. We're gonna have a 0xdd with a 0x05 mother RAM with a 0x04, 0x00, 0x. Well, this is it's a 32-bit, isn't it? So it has 3 of them in that order, and that's the way, you know, we're gonna get it and stuff like that. It's perfect. Anything's gonna happen in there, you know, it's just the way it goes. We're gonna push it on that way. Let's compile. Let's see what happens. We do compile. So let's try to disassemble this instruction just the same way as we've been doing it before. So let's go back in here. You know, we're gonna see that we are inside the for loop. This instruction, defective bad size, we're gonna keep it the same way. It doesn't matter. Main buffer, rec buffer, this is the initialization process. We don't care about that. Mandatory prefix, there's no mandatory prefix in this case. There's no REX as well, so we just keep doing the same stuff here. Now we go to the get mnemonic entry, and here's the interesting part. We're gonna go into get mnemonic entry and see what happens here. We're gonna modify the C byte whatever we found from there. We got that. We have a yeah, this is for the escape. And we can just say, well, here we have different case scenarios. You know, we have 3 byte up table, 3 byte up table, 2 byte up table, 1 byte up table, and then we make the check in here whenever we say, well, you know what, we get a valid manual byte because we say, well, you know, we have if we remember that if we had a 1 byte up table, 2 byte up table flag checking, we can also have the case that we have a group type of extension table, which we do it here immediately or explicitly, let's say. So we explicitly check for if we have an entry of this type, which is an entry inside this table, sorry. And yeah, I mean, that's all we do. If we find out that we have something well, if we didn't find it out on the manual byte for the group type that we first tried to do it, we go and look for on the extension table. If we find it out, and that's pretty much it, isn't it? And then the C badge just get added there, and the entry index, I don't remember if, let me put it to the note here because this is important. Here we return rule entry if entry index equal to entry invalid. which if we go and find it, what? There you go. So we have, here you go. We have entry value equal to 0. That means that we do have on the initialization process, where is it? Fetch memory. Here you go. We do have here. Let's see. Yeah, we have a null entry on the entry thing case. So if we go back here and we go to get entry, get mnemonic entry, yep, we got it, and the entry index, yeah, okay, perfect. So basically we have a table of entries and we have a bunch of tables, a bunch of specific mnemonic checkers, you know, like this operand, this up-byte match tables that we could basically go in and make that check with the get entry index. You should remember, if we have something in that table, we just return it. If we don't have anything there that it matches, we just return the null entry, and that's pretty much it. Okay, that's good to remember. It's good to have it there, because a null entry if the entry index equal entry invalid. Okay, perfect. Yeah, because we have entry invalid, remember. Okay, good. So we can just pretty much have the same here, you know, because even though it's another table, it's pretty much the same stuff, you know. We can have a entries in there. I don't know if we want to. It's the modern byte, so we have two modes here. I mean, we have 0, 0, 0, 1, 1, 0, blah blah blah. We can have, now the difference here is that we have two cases instead, so we have to just have a better way to do this. So I think I was thinking also that we can try to do this like this, you know. Let me show you, so that where is it? No, these are the tables. I want the disassembly state. So if you remember, we got I don't know why we have this. Do we compile if we don't? So EagleFly open model elementary. We don't use any stuff, any translate address. Yeah. We can erase all this code, but for now I'm just gonna keep it like this. And this should be something like that. Well, I'm gonna start like, we don't need this, so just do that. Everything should be nice and clean. You don't need this anymore, isn't it? And we pretty much don't need anything of this. Okay, so whatever. So I want to erase this stuff, which we don't need. Well, probably the tables here. Well, I'm gonna keep it because whatever. So I'm gonna add here. Oh, the thing I want to change now is that, if you remember, we had on the tables the EagleFly table group has these up by entries, which by itself is the matching tables that we use. So up by entries, even though I mean it's nice that they are there, we don't need them to be there. You know, I mean they can be here. So let's first try to make this change and see if we can see it working. Pretty much, let's see, let me think about this. The by entries, the byte's gonna be repeated, the entry index shouldn't be repeated. The flight table group is gonna have 256 possible entries, and that's pretty much it. I feel like I was just thinking, well, yeah, that's cool. Yeah, I mean, here we're using a lot of stuff, but we don't care how much, say, size right now. So let's say that so let's go that way. Let's see what happens. mean, the first thing, like, I mean, I like the representation of it, but well, it's the same. So let's see here, all by entry index. Now the case here would be that this whole stuff would be the same. Let me just go a little bit here, fetch memory operand, get entry index, fetch memory operand, oh, okay, it seems that we need them. So we'll go to the up by entries up indexing here. So we have the group type, and we just get the group type here, which we got, which is perfect. And then we can say group, and this is system state by entries plus group first by entry plus up index. You know, this is the offset that we have to do to get to the first one. The other thing is the same. Then now this is the up by entry byte. The entry index is gonna be blah 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 to get the result, and that's all she said. So we compile. It's not a member of EagleFly Disassembling state. How do we call it? Okay, by entries, we're gonna say up by entries, because why not? And here it's gonna be the same thing. Disassembling state up by entries plus group first by entry plus by index. A little bit more complex in this case, but we don't care, it's just the same. Probably is more simpler because, okay, that was the only that was the only difference. Now this is for the checking, but of course we have to make the change as well. In here where we say that we're gonna, this is the initializer, isn't it? Yeah. So this is the entry initializer, which is alright, that's good. And we have to initialize as well the tables for the up by entries. So it's gonna be, this goes for the groups, and if I say group disassembling state group type up by count, it's gonna be that first by entry equal b, it can be group index, I guess. Group up by count, and now and we can say, well, we have entry index, this is okay. I will use another which is up by index, and pretty much this is up by index. Okay, I'm gonna call this index, and then we can just say that we do the same here. Up by index plus plus, you know, whatever you are. Probably the up by index as well wants to be nullified. No. And then we just say, well, we have a first by entry, which is first by entry index. So it's gonna be first up by index. That's pretty much the thing. And then we just pretty much say, well, this is pretty simple right now because we're just adding one. We're gonna change this later, so it handles more of them. So we don't even need this loop anymore, isn't it? You can just say, well, you know, this thing here and this thing. Well, I'm gonna keep it. Oh my god, because why not? So yeah, we got the first by entry, by index, from by count, which is okay, and then this is index, and this is first up by index, and this is b entry, byte of bytes, entry index, and then here we have to add as well the main of byte. Now this is kind of interesting. Well, before doing that thing, entry index, that's okay. B entry, entry index, perfect. And that's pretty much it, isn't it? Okay, so let's compile. Of course, this now has to be called first up by index, and that's pretty much it. Up by entry, this has some state, update up by entries, and this first by entry is first up by index. See, there we go, and that's pretty much it, isn't it? So let's see if that works. You know, let me go to the disassembler. Let's go to the debugger and see what happens in there. You know. Here we go. Alright. So let's see. Let's put breakpoint in here, you know. Now, well, let me erase the instruction string for a bit so that we can just do the same thing we were doing before. And I'm gonna put breakpoint in there, and let's run this. So there you go. There you go. We have I don't know which instruction is mandatory prefix. No. So I don't have that. Doesn't matter. Go to the mnemonic. Let's see. We have OF, but it's a simple, so it's a 2-byte table, which in this case is not, because it's the special opcode thing, I believe, is the extension one. So if you go to the entry index and stuff like that, now the group type, disassembly state, of tables, of table groups, group type, there we go. We go and look at it, and then we say, well, group first up by index is 2. Let me change this to, well, it's the same, I guess, but it's not. So 2 up index is 0. So let's see if we got something there. Up by entry is up by entry is entry index 62, and the by is 164. Well, A4. So the up by we are looking for is 01, which is not the case. So we pretty much go away, and we know it's invalid, so we go and find it out on the other case scenario. You know, this is gonna be first byte of index for the group. The group is so 4, that's good, and then we just say, well, up by entry it's so 4 now, and it's C3, and the by is C3, and the one we're looking is C3. That's correct. So yeah, it seems to work. Result up by entry index is gonna be the result. We go back now. Now I think about it, we are missing there a break in there, so we don't want to go and fetch other. So right now, because since we just have one, we haven't caught that bug, but now that we see that, we should change it. So let me go get entry index, and we should do that. Alright, so I'm gonna pretty much do the same stuff back again, you know, because why not? Boom, boom, boom. See, bye, there you go, same stuff. We're gonna enter in there. Let's see, we got it. We're not gonna there, we're gonna enter in there. So let's go and see. We're gonna go and find it out. Here we go, we're gonna break. We got the result. The result, it should be an index, you know, 04. And there you go, entry index, cbyte, and the main of byte. It's gonna be something there, you know. It modified it. The entry index is 4. The result now should be some entry, which in this case is VM resume, which is, yeah, that's correct. That's the one we were looking for in there. We got this about entry, mother in present, print instruction, and we just have the instruction being resumed. That's okay. We go once more time here. We see that this is another one. We entry, we got everything there, and we print instruction. Let's appeal line XMM0, XMM1 away. That's perfect. So it seems to work. Let me see another one here, the same. You get the mnemonic. What about the entry here? I want to see it. Is a shield instruction. That's correct. We got for the shield there, and we just print it out with a shield with an address EX03. Perfect. We go back into there. Let's go one more step one here. We got for the entry, and well, let's see what happens in there. You know, it's valid 0x00, 0x1. We don't use this value, but whatever. And I'm gonna get, it's an add instruction. That's perfect. We can just do the same stuff here. Print instruction, and we got an EAX003 within address operand, memory operand, sorry. And if we run it continuously, we should assume that we got everything correct. Okay, that's perfect. So that change, little change we did there, but you know, it's just like collapsing the data information into one big table, and that's pretty much it, which is going to be useful because it's going to be faster to look up in most of the cases, of course. But since now we have contiguous data, we have that kind of, we help the processor to fill the cache line better in that case. And it's just a simple change. You know, you can do this as well whenever you want. You know, if you want to fill the cache line with the most relevant data that you're gonna use. In this case, we use the byte entries. You know, the byte entries are the most common case scenario that we're gonna that's gonna happen. You know, is the first call to the entry. The is the first thing that we go and look for whenever we look for entries. You know, first we do the match with the byte entry, and then we can just go and look for the entry itself. So I think that's nice. So if we do the same here, so now if we do add the instruction now back, let's go and do that. Over here, let's go and do the same stuff. We're gonna add instruction. So the instruction is gonna be another it's an entry, of course. It's gonna be, it can be another table and well, another group there, which should be because we use two ways of there. But let me think about this. Let me see the usage case there. So let me go to, oh my to get mnemonic entry, which is the case in here. So we're gonna pretty much make the same stuff here, you know. Now we can do that, I believe, in here, which if cbyte is equal to, well, 0x and we can call it escape, or we can call it FPU, FP. I mean, this is more more natural, let's say. I mean, we know it's escape, the escape opcodes there. Now, let me make sure that these D8s they go from D8 to DF. So yeah, well, this is D8. Okay, yeah. So they are, they are, they are, they are, they are shown here, but yeah, they are reserved for the escape to coprocessor instruction set. But that makes sense, isn't it? I mean, it's an escape to coprocessor. Now, if you put it that way, now I understand why they call it escape. But yeah. And yeah, so this is the 0, you know, the 8, the 9, the F. So pretty much is just this line, isn't it? This little line for once, and it can be for 2 as well, you know. If we go to D8, here you go, or not. Probably not. Probably, well, no, because they don't have OF, isn't it? Yeah, they don't. If they have OF, then we just have a 2-byte table. But in this case, they are 1-byte things, I believe. Because yeah, if it doesn't, they should appear here as well. So we don't have escape up 2-byte escape up tables. You know, that's not a thing. And what about 3-byte? If we go to D8, D, yeah, and with 3-byte we don't have D8 as well. So it's just 1-byte stuff, you know. So we can just make the check up front, and we are gonna be okay. So escape up table, why not? We're just like playing around with this, and then we just say, well, you know, this is the thing, we're gonna go and look for it, and the main of byte is gonna be pretty much the same here. I could do it afterwards, but it's okay, it's more. So if you do that case scenario, we're just gonna keep it that way. Now going forwards and go and look to that table with the get tree index, and we should look for it. Now we have to be careful here, because now here we count for the mother m, we're gonna go and look for the mother m as well, which is in the entry index. We're not gonna, this is a special thing, we have to understand if the mother m can serve other purposes as well, not just for the extra extended encoding thing. But I imagine something like, if group type, let's say, well, let me put this in here, get entry index, just goes and fetches in the table, and that's alright, that's the thing we want. But if group type equal group type state cable, we have to say first, you have to resolve the mother m, because the mother m, we can have it just joined together, isn't it? Well, we have escape, we have that, we know we have it on the first one because it's stable 0 0 to BFH. So BF is, let me see, 1 1 1 1. So we go and look CF, we have 1 1 0 0 1 0 0 0 0. Okay, so those 2 bits, C you can just say now here is, since we are using here the mother m by, I'm gonna put it here. So my question is, can we include it on the same table? Probably probably could. Now the problem would be, of course, so this is the for EST0, ST1, ST2, okay. FST, FUCOM, FSTP, FUCOM-P, store, compare, store, and pop. In order to compare and pop, so yeah, I mean, it's not like too hard to say that, but of course the thing that we are looking for to match with should be the value, you know, because yeah, I mean, this value is different to this value, but the value we are looking for, we have to make the decision of which value to choose from, and go and get that, you know. We can use the same table, but just we have to resolve it. Yeah, I mean, that's one way to go. So we can just say as a pre-pass that we have here, you know, we are gonna use the main by as the result, or the by, let's say by match. Test byte, and then we say test byte, so it's gonna be the main of byte. If not test byte, it's gonna be another case here, which is the main of byte shifted by the mother and byte shifted by mother and byte shifted by 3 and 0x3. So we can do that, and then this is going to be Well, we can keep that way, I guess. Yeah, we can do that. I think we can simplify this a little bit more, but we're gonna hold down there. Good size, scale table, we're gonna have that, so let me go to and add that as well. I don't know where did we define them. There you go. So we just say, well, we're gonna have another table here. This is gonna be the upscape table. There you go. Now I think about it, well, all these things, I mean, it's good to have it, but I think it's better if we do it on once we know that we are not gonna modify it anymore, because we have to modify them all the time. So yeah, that's good to know. So let's do that, and we say, well, you know, we got this is a UNAT. Okay, so okay, so yeah, we use a UNAT. Okay, not bad. Now I have to be careful with the main of buy, because we shifted here, so the C buy is gonna be used by the main of buy, you know, and whenever, for example, here we shifted the we can just do this. Now we can do it more like this, yes. Test buy, modern buy, and then we just say main of buy plus 1. And we want to move past by there, because we also, I mean, it all depends, because if it's, let me see, in this case we don't have anything else but the displacement, so that's important, because the displacement, it's there. For example, let's say, yeah, that's the next thing we're gonna do. We're gonna disassembly one with some operands there, so let's say an F mul or something, so we can see better what we can do there. So in this case we don't have it, so we can just assume that it doesn't, but I mean that we don't have any encoding on the modern buy as well. It should be, in this case we don't, because we use the whole byte to encode that case, but in this case where we just use the NNM field, we have the modern field free, so probably there's some encoding there that we can have in there. We can even check it here, you know, we can go to the floating point instructions and try to find one. This is general purpose, general purpose, general purpose, general purpose, granularity MMX. Where's the X37? This is P6, this is SSC, SSC, SSC. So it should be somewhere, isn't it? I mean, if I say fmol, let's try to find it somewhere. Fmol, 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 fmol. There's instruction. This is encoding. This is the table. Aha, here we go. Aha, we get okay, these are the floating point. There you go. This are the floating point. Oh, okay, hold on. Tail shows the 5 different formats used for floating point instructions. In all cases, instructions are at least 2 bytes long and begin with the bit pattern 11011. That's correct. That's totally correct. It can be first or second byte. The first byte is gonna be 11011, and then this is the mother RAM thing. And optional fields, we have the SIB and the displacement. Okay, so yeah, the mother RAM is there. Then we have oh my god, OPA. What's that? OPA. P is pop. 0 do not pop stack. P stack after operation. Okay, these are why the terminal refers to. Okay, these are XMM and rack, XMM. Yeah, this probably is, these are vectorized ways. So it's after the vector instructions. So floating point instructions formats, okay, they are special in this case. So we have OPA and math, 1 OPA and math, 1 OPB, RM, OPB, RSTI, OPOP, DPOPA, OPB. Okay, what's that? That means a combination of this. Memory format is MF. Where do we have MF? Oh, here. Okay, 32-bit real, 32-bit integer, 64-bit real, 16-bit integer. Okay, then we have a pop, do not pop stack, pop the stack, and then the destination is ST0, the destination is STI. Okay, and R XOR D equals 0, destination OP source, source OP destination. Okay, like what? The modern ARM fields of the mother and byte have the same interpretation as the corresponding fields of the integer instruction. The SIB byte and displacement are optionally present in instructions that have mod and RM fields. Their presence depends on the values of mod and RM as for integer instructions. Okay, that's the same for as integer instructions. Table B39 show the formats and encodings of the floating point instructions. Okay, for example, FAPS, you know, this is blah blah blah. Shit's correct, you know, first bit. And then there's 001, 1110, 001, there's, okay. Compute 2 to the ST0 minus 1 is 2 to the X minus 1. to the x power. Add and pop, main instructions. F compare real and pop. 32, 64 or STI. Whenever it's in memory, we use the mod RAM. Whenever it's STI, we use the STI is encoded in there. So that's interesting. So that means either they use the, this is an extension, of course, and one should be set because it's a register. So they always, they always are at least 2 bytes, and they use the mod RAM. Now we also need to decode as well the data that is in there. It's a little bit weird, 1511 1098 7, and then this is the first byte, this is the second byte, this is the mod RAM byte. Normally we have a mod and a RAM, and we have a one OPB or the whole OPB, or we have an OPB on here, and then we have an RSTI in there, or we have OP and then all bits set in here once, and 00, or OP all bits set until the 9th bit, and then 0 there, and then we'll the same. So the only one that has a D or a destination are encodings number 3, STIR. Now R, I don't see R XOR D equals 0, destination OP source, R XOR D equal 1. Okay, R XOR D if they are different, there's gonna be 1. If they are the same, there's gonna be 0. So if they are the same, the destination OP, what is OP? Can somebody tell me that? Operand, destination operand source. Oh, I know where the definitions are. Hold me a second. I remember. Here you go. No. It's at the beginning. Oh my god. Here you go. These are the general purpose. Condition tests. Oh my god, it's not here. Oh my god. So it should be. Oh, here it is. No, this is the condition test. No, this is not. Oh my god. Special fields, upcode fields. Oh no, we're not care about them. We are not. This is not the case. My god, somewhere else. No. No. We haven't checked this before, but yeah, it doesn't matter. We're gonna do that as well. But FX store, the SSC instructions used in Motherram. So yeah, they don't tell me where OP means. I thought it was there. Gotcha. Well, there are a lot of instructions. There are a lot of instructions, isn't it? A lot of instructions. So yeah, well, we don't know, but doesn't matter. We can check that later. Yeah. So the R is because if you remember, we have the reverse forms of the instruction. So the reverse, the R, remember? Oh, okay, I got it. So the R of the mnemonic, the R of the mnemonic is this R, you know. So the R is encoded here, literally, and literally. Is it literally or literally? I don't know. Well, it's R. We have the R. So if the reverse is 0 and let me think about that. It makes sense since, you know, normally we have dest, source, dest, you know, like dest equal dest. Let's say a subtract instruction, you know, dest equal dest minus source. That's a normal instruction, let's say. So we are gonna have the destination bit is gonna be 0, the R bit is gonna be 0. That means that the XOR between them is XOR D equals 0. Destination OP source, that's okay, OP is the operation that's gonna happen, you know. It's like destination minus source. Okay, and it's stored on destination. So R, if you see here, only happens when D is present. Yeah. We have P, which is the pop thing, which is another thing as well. Yeah. We have OPA. What is OPA? So the first operand, it means the first operand, and then the second operand, operand A, operand B, probably, you know, first operand, second operand. Okay, so the first operand is stored. Oh my god. For example, on FLD, ST0 plus 32-bit memory is gonna be memory no, but what? Remember that is the extended operand, or is it main op by, isn't it? It's the op by. It should be the op by, you know, because are extended, remember, so they should be encoded in here. Now remember that it goes from C0 to CF to FF, sorry. That means that these bits are set. That's correct, all these ones. So these are from 3 to 5, it's C0 to EF. The other ones, these two, are the encodings when for the first whenever we are in the range of 00 to BF. So this is 00 to BF, and this is C0 to FF. So normally this is C, and this is 0. Well, it can be 0, it can be anything. So the encoding for why did I put this thing? Okay, whatever. So for example, let's say we take the little thing here whenever we are on the range 00 BF. So that means that rather we have one OPB yeah, I mean, this is like a little bit weird because I don't know what it means, you know, but probably it's telling me, I mean, this is a mod 76 543 is the rec field, so it's telling me that the rec is having one set and the OPB, or it can be the OPB complete, which I mean, this is the normal case we normally see, but no, sometimes we have OPB just with one set. That's kind of weird, but yeah, we have to see an example of that. But yeah, the normal case is OPB whole set, and that's for this part, and this is the DD, DEF, you know, K scenario. So it's gonna be MF, OPA, oh my god. Well, I'm gonna hold on there. We don't need it right now because the instruction that we are decoding is not like super relevant. We can, this is gonna serve the purpose that we want. So, oh my god. Oh yeah. So this is like that. And this is like this. Yeah. So the problem that I was like thinking about, well, we have to move this. We have to move the manual byte. So we should not move the manual byte in this case, because I mean, it's gonna be just manual byte plus 1. You know. It's gonna be test by, I guess. Test by. Test by. Test by. and then I think that's okay. But here we're not gonna move. I mean, we can keep test by, like this. And then now I'm not really sure about this. Yeah, I mean, probably here we can just not move either. We move right now because the instruction we are using doesn't have any problems at all. But probably it's just the same case as this one. So we should also change this one. So that we don't, I mean, we don't want to move the pointer. We just want to return a valid pointer, let's say. So we can just say something like this. Instead of using pointers, I'm going to use offsets. Why? Because I think it's way much better. So let's go say something like that, you know, and then, you know, it's gonna be, this is gonna be main of by plus offset. So normally, well, we can say offset is gonna start by 1, and just say, well, I'm gonna say main of by plus offset. I'm sorry. Now the value the value we want to check in here, of course, is a little bit special because it's just not an offset, you know. So probably, yeah, the resolution of it's good, you know, the mother and by. It's just like, hey, we want to check the mother and by here. So yeah, that's the special thing of this, that we're checking the mother and by. In this case, it's the same because we're checking the mother and by as well. And well, for now, I'm just gonna say the offset. And here the offset, we don't want to, this offset is gonna be equal to 1, and here offset is equal to 1, isn't it? Probably here offset is equal to 1 as well, so we're just gonna keep it like that here. So we're gonna say now well, yeah. But we have different tables, isn't it? We have DD, we have D8, so this is like DD, So yeah, so my bad, my bad. For now, well, I'm just gonna keep it simple for just like that. We don't need this anymore. In fact, I can move this. I don't know if I can do this. Well, it's a little bit. Something more like that. And call this down. And we could, now I think about it, we could pass this up front, you know, like all these things, since we're already doing it before, so we just say can just say this. We could try it. So it would just be immediately done, which I think is okay, you know? So we don't need to type anymore, we just like do the thing. We just go and get the entry index, which is I think it's okay, you know? It's not that bad. And we can get rid of a lot of old stuff here, you know? So we just say, well, you know, we say group type is blah blah blah, and then mother and by it's gonna be main of by plus 1, and then we just make the resolution of what the mother and by. I'm gonna move it out so you just use it, and then we just say, well, you know, we're just gonna make the check for it here for each particular case. Now the D, of course, type is the D, and if the mother and by is gonna be outside the range, we just say that, sorry, inside the range if it's inside the range. And probably, I mean, this is not like super I mean, it's fast to see, but sorry, it's not fast to see, but see, this is for 0, so it's just looking for the 1 minus the least most significant bit set. If it says we are out of range, you know. Wait a minute. No, that's incorrect. Yeah, I'm sorry, my bad. So yeah, let's do the simple stuff here. So it's gonna be if mother ram and mother ram by there you go. Now this offset, we don't need it anymore. Just gonna break in there, and then we're just gonna say, well, you know, we got the entry for this particular one. So we can just say, well, test here. It can be the mother M or the manual band, you know. Or can just say that. There you go. And that's all we need to do with that case. Now let's try and compile this. code compile. Just do the same thing here. Let me erase all this stuff. Entry index. This has to be moved upwards. Okay. So let's try to make the case here. We can just keep, let's say we can do this. Just the same way. We don't need that. We just say we don't need that. We don't need that. We don't need that. We don't need that. Just do that. And this is just a special case for the extension table, where we just have one by op table, stuff like that. Which we could do the checking for each one, but I think that's okay. So we have a checking in there, we have a checking in here as well. So that's pretty much it. It's all up table entries, entry index, okay. Now let me compile this. Test by. We'll have it here. Just have it here, so we're gonna move it. Now of course this is gonna be it's gonna be an error, but we can say something like this. which I don't know the particular cases for each one, but let's say we have something like that. And this is gonna be something like that. So yeah, I mean, it's pretty much the same thing now. We just throw it all away and just put everything inside here. We can also collapse this a little bit more and move each entry here on here, you know, since we pretty much don't need that. But for now I'm gonna keep it that way because we're getting ran out of time. So let's try to disassemble that. We're gonna just do the same stuff here, you know, we're just checking there, and then that's the same thing here. Now I move the main out by here because that's important. In the other cases I didn't move it because that's the only case for now that we see that we really don't care about it. So we just do that, just move the resolution, and that's it. So let's go and test that, see what happens. Now, oh yeah, we have to fill the entry, so let's do that as well. So let's say over here, let's add another entry as well. We just say, well, you know, we're gonna have this is gonna be how it's called, FL entry. Oh, FLD entry. And this is just same, and this is gonna be rect to mother RAM. Rect to mother RAM here, we don't have that. We do have a mother RAM, so let me do that. Well, we don't in this, well, let's say false, because I mean we do have a mother RAM, but in the special meaning. So yeah, probably we want to do something better there, but yeah, rectum mother RAM, we don't have anything of that. Immediate size, we don't have that. Register operand size, we don't have that. It's FLD, let me find it. Here you go, FLD load real. Is this one? It's all, yeah, it's 1111 101. So this is the DD, that's correct. And then we have memory operand. So all it can be a memory operand or STI. So how we know it's a memory operand? Because it's from memory. Probably it should tell it here as well, isn't it? Scale up goes the DD. Here we go. It just says double real. it doesn't tell me if it's a memory operand or whatever. Which, I mean, it couldn't tell that, but because right here we just see, I mean, we know it's memory because here it says memory. SDI in their case is gonna be, if it has to be double extended precision. So yeah. And the SDI is encoding there as well, you know. And for 80-bit is 101 the encoding there. Okay, so yeah, I mean that's pretty sane, let's say. So load +1 to, yeah, we don't care about that. Okay, so that's the encoding. So we do have a mother RAM, so we do have to check the mother RAM. Because we have a mother RAM. So let's go to the mother RAM and see what happens. We are on FLD addressing forms, and normally we have a 05 there, so it should be a displacement 32. So yeah, so we do have a thing there. So we can just follow the same idea because we have the same thing. Yeah, so we can say mother M prism because the mother M is gonna tell us that. Sorry, it's true, and it's let's follow the same idea for the add. We don't have any rectum mother M as well here, so you can just say the same thing here. Immediate side register, operand size, all this can be invalid operand count, which is, we do have an operand, it's 1, and the mnemonic name is gonna be FLD string, FLD some string, FLD string. There you go. So yeah, we just add that. Let's add the group types here as well. So let's say abstention table, and then this is type scale up to DD, and then here we add that a thing here which is DD. Well, sorry, this is 05. We're gonna encode that as well, but we're not gonna move the pointer. So that's a tricky thing to follow. You know, right now we don't have the answer, so that's why it's like a little bit junky the way it's structured out. But yeah, so we check the mod ref because it just works the same as the extension codes. I'm gonna put here extension codes. Some instructions need to check the extension codes. For mnemonic entry matching. Okay, so it's gonna be a 5 as well, you know, pretty much the standard way. The bytes we use it here, and the group types we use them here. All right. Okay, perfect. So we already added the entry, so we can just play around and see what we can do with that. So let's try to disassemble. So we start by there, you know, we got it. The C byte doesn't have any mandatory prefix. This is the same. We have anything like that. We got the C byte, blah blah blah, entry invalid. Here you go, the group type, blah blah blah. So we don't have anything but that, so it should be something like this. Same the main of byte, something like that. Is 1 byte of table, and then you just say the mother and byte. Well, we have a main of bytes. Is DD, perfect. So the test byte is the thing we care about. So yeah, we have a DD there, so that means that we have a group table DD, and then we say, well, you know, we are gonna check for the mother and byte. The mother and byte is 05. That's perfect. And yes, we do. That means that we are in the range of that. That means the mother and byte now is gonna be just that. That means 0. Okay, that's correct. And we just have a test byte which we use. The test byte is gonna be the one with the code, so we go and try to find that. Now the group type, sorry, let me move a little bit. Yeah, with the group type we changed to the DD, so that's correct. Okay, that's correct. So let me move a little bit there. There we go. Okay, so we could do there. We got the group. There we go. We go to the entries. First up by index is 5 plus up index, blah blah blah. Now the y is so 5, and the O byte. Oh, we didn't change the O byte, isn't it? Let me go. Oh, my bad. I wrote the wrong thing there. Since we are testing the rec field, not the mother, so we have to be really careful with that. So where is it? It's in here. So this is not 05, this is 00. Some instructions need to check the instruction codes for mnemonic entries. For mnemonic matching, they can be like, let's say, they can be the mother M, or the NNN, which is the rec. So this is I can say mother M by NNN field. So yeah, I mean that's because of the way we make that. So one more time. There you go. Oh my god. We got a valid entry, let's see. we got the FLD, perfect. That's what we wanted. Now the pointer, I don't know where the pointer we're looking at. So let me rewarp here and do it once again because I want to enter there. Continue. F11, which do the thing. There we go. We have that. We just do rewinding here. There we go. Now the test by. It's gonna be that. We make the checking. Go find it out. We do, since we find it out. I am assuming that we're gonna find it out there. Yeah. So there we go. Go to the break. Return result. And we'll have that. Now the main of buy is blah blah blah. So yeah, we'll return the we are pointing now to the mother RAM. That's correct. And we got the result. That's correct. There you go. We have a mother RAM present. There you go. That's correct. Begin operand extraction. Okay, let's see what happens in here. Extracting operands, CO by. Okay, normal stuff in there. Fetch memory operand. This is the one we care about because it's a memory operand. So we just say, well, we have that, C entry, mother and by, do stuff, operand offset. If it's from C0 to FF, it's not. It's 05, so that's not the case. Now with mother and by, it's from 00 to 3F. That means that the address size it's 0. If mother fields mother and blah 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 blah, here's to go. So displacement 32. That's correct. That's the thing we were doing there. Effective address size, if effective address size. Just do that. Displacement, the same thing here. Just do the same. And we start to print it out, you know. So that's pretty much normal. We can just go out, return buffer count, and there you go. Now my buffer is 04000. Now of course this is bad because it should be the other way around, you know, since it's little endian the way it's encoded. So I'm gonna do that just after we see the printed out, you know. We go to the immediate now we're gonna fetch the register. We don't have any register operand in there. Well, we do. I mean, this is assuming that we do, but we shouldn't make the check-in because the instruction it doesn't need to, you know. So we can just say we're gonna get something there, you know, something I don't know, something wrong course, EAX, yeah, push string to buffer, the way whatever. Now, oh my bad, this is a typo. This should be a registered buffer, still, well, whatever. Yeah, oh my god, that's totally wrong. What? Since we didn't use it, there's another typo there. So let me change that. So this should be this, and this should be this. So yeah, so that's this is this is wrong. So probably that means that we want to change the API a little bit there. So end operand size, that's correct. So let me just change that. Let me first change the memory operand thing. Let's say for the fetcher, now this is gonna be, it has to be the other way around, you know. Effective address size. we the displacement plus plus, this has to go from the effective address size -1 to 0, you know. And you know, this, you know, and this is this, you know, and that's it. Now I'm assuming that displacement is 182. We're passed by that, that's correct. And we're gonna be moving that just the same way. Now the other way around, of course, and pretty much the same stuff. Pushing backwards and just the same way around. That's correct. And that's all she say. Okay, that's correct. So let's write that. Now let's change this as well. The fetch, this is the memory, this is the immediate. Fetch register operand. Now this we want to say that here we pass register operand size. You can say entry register operand size. We said that. Where is it? It has invalid. Now what is the invalid? It's 0. So it shouldn't enter, isn't it? Register operand size, memory operand size. All it's invalid here. Probably this should be something else. We're not even using it, but it shouldn't do it. Now, well, let me compile and test it. So let's run this one more time. I don't care about that. There we go. Enter. Begin extraction. We happen to have an exception violation. Read access violation. Displacement was blah 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 blah. It's F. Oh my god. So that means that we overflow the UN 32 and that's of course because okay, I see the problem. So we can just say where is it? This is gonna be a then. That's the whole thing. Of course, we're not gonna have displacements greater than something, so the sign is okay. There you go, main buffer. Now it's correct. We have a 0004 displacement, and then this is, let's see, it's invalid. And here as well, we okay, we passed effective operand size. So this is the problem. We passed the effective operand size. Because yeah, I mean, this is okay just because other instructions need that kind of override, you know. But you know, so I think it's better if I just say okay, that's what happens. So what we can do, of course, we don't have EAX. There's just one operand. So let's say we can add another thing here, like Because if it was the case that it was like the whole byte, which is not the case here, we'll need to do something different there. But so yeah, for right now we're not gonna solve that kind of problem. But yeah, I mean we can say entry in a field. Now VM resume uses the same way, but since we said that it doesn't have any mother RAM, we don't have any problem with that. So yeah, that's the instruction. That's correct. So let's see if we print the other ones as well. This is the Vim resume. Okay, we didn't get it. Which is interesting. We are on 66. Hold on a second, hold on. One more time. I didn't see that. So we're gonna do that, boom. Now C byte should be pointing to there. Let's see, C byte now is pointing to OF. In fact, we can OF. Yeah, it's the OF that we happen to have here. OF 01C3, which is the next instruction. So that's correct. So let's go. We do have 1. We are on OF. We do the same thing. Let's go into here and let's see what happens. So if C by, we have OF create. No, we do have an OF. We have a 2-byte up table, C2 blah blah blah, and main of byte. The main of byte this is an extended opcode. That means that, let's see what happens. Can they be, are they mutually exclusive? We happen to have, well, we have that structure before, but let's see. So main of bytes pointing to somewhere 01. Okay, that's the main opcode 01. And we are using the 2-byte up table to try to find it. And if we go into there, we shouldn't happen to find anything. And that's, yeah, that's correct, we didn't find it. So yeah, so entry index is invalid, and group type is a 2-byte up table. So we should try to find it now as a as an extension, you know. And we pass the main of by, which is 01, and we should happen, I mean, if anything, it's correct at all. Oh, but we have to pass the mother M. That's true. So yeah, that's incorrect. My bad. My bad. So that means my bad. Over here is not this way. It's this way. You know, we don't care about the main of by here right now because we haven't tested with any operands. But I think we should check 2 operands, extension, 2 operands, adding subtractor. You know, we have to add more operands to see how is it growing this thing. So yeah. But for now, this is gonna be, well, plus plus, yeah. And then we do the reference. There you go. It's correct. Now this is gonna be the main of by. The only cases and areas where we modify it is with this, you know. If we don't find the entry index, of course, in the case of, if we try to find it out with this k up top table, blah blah blah. If we don't find it, of course, we have to go and looking for somewhere else. So we do that, and we try to follow for the 1 by, find it, we don't find it, we don't care, which so, and that's the whole story of it. Yeah, so that's the whole case story for that. And then we just do the same thing here. Now we have to move the main no by for think. Now test bytes never been moved. That means that it's always pointing to the right one there, you know. That's correct. So yeah. Yeah, so that's the only problem. So let's do it one more time, you know what I mean. The first one we already done it. There you go. Fill. There you go for the second one. Mandatory. There you go. Let's see what happens in here. We know that it's an OF escape. You know, a mandatory prefix there. Well, it's not mandatory. It's just it was the skill up code, isn't it? Well, whatever. So this is a 2 by, yeah, manual by, blah blah blah. It's not gonna find anything else there. You know, should be that entry index is invalid. There you go. We try to find it out there with the manual by. So let's see what the byte is. Is it 3? That's correct. That's the thing we wanted to. And we try to make the matching here. We just let's try to see what we got here. The byte is it 3, and it's a 3. That's correct. We got it. We do break. We just resolve. There you go. And the manual byte is going to be moved past by the multiple byte in this case. You know, so it should be manual byte C3. See, yeah, +1. So C bytes, whatever that thing. Okay, perfect. And result, blah blah blah, correct. Entry, perfect, correct. Well, let me see the entry. Yeah, it's a VM resume. That's correct. If the entry modern present, it doesn't. So we don't do anything there, you know. And I think that's all, isn't it? Because if I see correctly, yeah, the C3 now will pass by there, you know. Okay, so we print instruction and VM resume, perfect. That's all she said. And let's go to the next one. Let's see what happens with this. We are, if I assume we are on the 66, yeah, we're on the 66. That's correct, my darling. And there you go, mandatory prefix, whatever, we don't care about that. Then you go to the mnemonic thing. There you go, there's a C by. There we do fancy stuff with there, you know. And we find out it's an OF3A. There you go, and pass by there. We got the entry index. Let's try to find it out. I don't know. Yeah, we do the match. We return set. There we go. We'll have that. Just say that. The entry is a P line. Perfect. We do something with it. Yeah, we have a begin operand instruction. Don't remember what happened to be here. You know, something. Yeah. It's a register operand, so we have to go and fetch it further, you know. There you go, further, you know. There you go, we do the printer. This should have an effective operand size that's valid. There you go. Push string to buffer, whatever, there you go, print instruction. And yeah, that's correct. XMM0, XMM1 away. Let's go one pass by. Continue doing the same stuff as before. The same thing. I don't know which instruction we are now on to. Let's see the C by. It's OF, which is correct. It's OF. The instruction there, so we can just go in there and see. Try to find something interesting. Let's try to see. It should be this one, a 2 by up table thing. So we got the entry. Did we do? Yes, we do. And we just try to find it out. I don't know what about that. Let's see, the entry is a shield instruction. Perfect. We begin. We have a fetch memory operand. I think this is a memory operand, yeah. So we can just do the same stuff. And yep, that's correct. XMM0, 00, AX03. Perfect. Let's go to the next one. You know what happens. C by should be something different now. It should be 03. Yeah, you know, it's this instruction. Well, I don't know. Yeah, it should be this one because this is the immediate. So yeah. Okay, Rex prefix. There you go. Valid. What about the entries and that instruction? There you go. They got the memory operand, the immediate operand. We go and we print at EAX blah 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 blah. So there you go. We add another instruction there. That is a floating point instruction. You know, this is the beginning of something really special. But yeah, you know, I mean, we are getting up onto, whoa. Oh yeah. For example, here, we shouldn't have any mnemonic there, so it's invalid. Okay, perfect. So let's resume this, and there you go. So there you go. We have added another instruction now. That's nice. A really simple instruction, by the way, but yeah. Yep. So I think we're gonna stop here. But hey, don't worry. Now we're gonna pass by to the next, and you know, probably on the next stream we're gonna start playing out with. We have to play with the operands. We have to add instructions that have lots and lots of operands, so we can just pump that out, you know, like, because right now it's all that quirky stuff, but yeah. So that's what we're gonna do in the next stream. So today I would say, please, if you have any questions, post them on Twitter or YouTube, and I'll be there to answer. Yep. I would say thank you very much for coming up on this stream, and I will see you all on the next stream. Thank you. See you all, and take care.